All right, guys, so let's go over this. Question number 1, list the 4 points of the atomic theory. Obviously, it's out of 4. So, okay, our first point, okay, all things are all matter made of atoms. If they have something along those lines, that's good enough. Okay, that's essentially the idea of the first point, is that all matter is made of atoms. Okay. Second point, okay, atoms of an element are identical. Okay, and obviously atoms of other elements are different, so they have something along those lines. Okay, that'll be fine for that. Okay, for 3 is about them combining in whole number ratios. Okay, and number 4 basically talks that you can't change an atom in a reaction. Okay, something along those lines. If they quoted them verbatim, that's fine. Okay, good memorizing. Okay, but you didn't have to. As long as you had the general idea of the 4 points, okay, you'll be okay on that one. So 1 mark each for the 4 points. Questions on any of those? All right. Who devised this theory? John Dalton. Okay, and in fact, most of the time in science, if you give us their last name, that's good enough. Dalton. Okay, name and describe the particles in an atom. All right, somebody give me one. Protons. Okay, description of a proton. What would it be? Okay, either one of those would be fine. Okay, they don't have to have both, but either one of those would be fine. I was just thinking positive and in the nucleus, but okay, that's even better. Okay, next one. Candy. Awesome. Okay, so negative, outside, nucleus. All right, and last one. Neutrons. And where are they? Good. Okay, so 1 mark each for those. They do have to have the description right to get the whole mark. Okay, if they wrote protons and said they were negative, it's wrong. Okay, because either they don't know what protons are or they don't know what the charge of protons are. Either way, they don't know enough to get the mark. Okay. All right. Number 4, sorry. What particle did J.J. Thomson discover? He discovered electrons. 1 mark for that. Okay, because he was the plum pudding guy. And number 5, who proved the existence of the nucleus? Ernest Rutherford. All right, and a picture of de Broglie's model of the atom. So I would go like this and go positive, positive, neutral, neutral, just so there, I know that you know that protons and neutrons are in the nucleus. And then I would have just done this. Cloud. You guys were like being way too detailed. I could hear it on your drawings, but that's fine. Okay, as long as they have a picture of the electron cloud model that shows that the nucleus has got the neutrons and protons, they're good. That's. Oh, that's fine. Yeah. Any other questions there, guys? All right, so we're looking at what here? 1, 2, 3, 6, 7, 11 points. Okay, so give them a mark out of 11. Let them see it, and then if you can bring it up here, put them in a nice, neat pile. Okay, so while you're finding that in your notes, just a note here on the quizzes, right? Obviously, I record the answers. Okay, that's part of the podcast for the quizzes. So obviously, I won't be posting that until after period 4 writes it. Okay, but if at some point along the way you don't do well on a quiz, you can always go back and review it later, okay? In two ways. You can try and remember the date, which is probably not going to happen, or in Power School, I always put a link to both the quiz questions and the podcast of the quiz in the task itself, okay? So when you're going through your Power School, you can look at individual tasks. You guys have seen that before? Okay, and there'll be two links underneath. One will be to the questions and one will be to the podcast of it. So you can click on either one of those if it's a quiz you didn't do well on and go over it again, right? Which I would obviously highly suggest. Okay, it's not like it takes very long. You don't have to watch the whole class. Just watch the podcast of the quiz, okay, and then move on from there, right? But it's a good idea to do it. Okay, so we've got naming compounds here. So most of this is going to be review. Right? We'll add on a little bit to the naming of ionic compounds when we start talking about polyatomic ions. That's these fancy things up here in this little box at the top of your periodic table. Incidentally, you'll probably want this out while we're doing this. Okay? So we need to be able to identify a compound as ionic or molecular, because obviously the rules for naming are different for ionic compounds and molecular compounds. Okay? So an ionic compound is going to have what in it? Metal and a nonmetal. All right. Now, how can I tell metals from nonmetals? Well, they put that little staircase deal on the kind of 2/3 or 3/4 of the way over the periodic table there. Okay, that runs down just beside boron, silicon, arsenic, tellurium, and astatine. Okay, that's the staircase that separates metals from nonmetals. Metals are to the left of the staircase. Nonmetals are to the right. Okay, so if you feel the need to label that on your periodic table, go right ahead. Okay. But that's what we need to know. For an ionic compound, if you got one thing from each side of the staircase, okay, you're looking at an ionic compound. If they're both nonmetals, it's a molecular compound. What is it called if it's two metals? Doesn't exist. Metals don't chemically bond to each other. All right? You can mix metals together in a process that will make an alloy, but they are not chemically bonded together, because if you heat up an alloy, one metal will melt before the other. Okay, so they're not technically bonded. Their physical properties are kind of retained, okay, within that mixture. All right, so we got to be able to write the formulae and the proper names for chemical compounds, okay, kind of at the end of the day today. Where did my pictures go? All my pictures are gone. That's really odd. Okay, fixed. So now we've got the pictures. So ionic compounds occur when a metal from the left side of the periodic table, non-metal right side, react to form a new molecule. Weird thing about ionic compounds is their bond. Okay, the bond between molecular compounds and the bond between ionic compounds are different. Okay, in an ionic compound, the bond is quite weak. All right, the reason for that is there's an exchange of electrons rather than a sharing of electrons. All right, if you are sharing something with someone else and both of your lives depend on that thing, you are very likely to continue sharing it and holding on to it very tightly, and thus each other, okay, and have a very strong bond between you. Whereas if your purpose in life is to get rid of this nasty thing that you don't want anymore, and the other person's purpose in life is to gain the nasty thing that you don't want anymore and hang on to it tightly, well, once you've made that exchange, there's really no reason for you to, continue to associate with one another. All right, so while ionic compounds will bond with each other and trade those electrons, the bonds break very easily. Okay, it doesn't take much to break them. All right, so that's why I don't know where I found this picture. It seemed funny at the time, and now it just seems really corny. Okay, the name's bond, ionic bond. Taken, not shared. Instead of shaken. I don't know. It seemed funny at the time, and now I really regret putting it on there. Okay, so we've got the fact that we've got sodium here and chlorine here. Okay, this is your typical ionic compound, sodium chloride, table salt. Okay, we're taking a metal. Okay, sodium is a metal and has a +1 charge because when it gets into a compound, it gives up an electron. So if we draw kind of a Bohr model of sodium, this is what it looks like. Okay, the first kind of shell of electrons holds 2 electrons. All right, that's that kind of circle that you saw in that weird diagram with all the teardrop shapes. Okay, the second shell of electrons has room to hold 8. So, like we said yesterday, we fill up the orbitals with 1 electron, and then after that we pair them up. Okay, so this shell can hold 8 electrons, but sodium has how many? 11. Okay, its atomic number is 11. So it's got this 1 electron in a shell that can hold 8 all by itself. Okay. Chlorine, on the other hand, chlorine has 17 electrons. Right? So its configuration is similar, except that its outer shell has 7 in it. Okay? Now, all elements want to have their outer shell full, because that way they look more like the closest noble gas. That's these things here on the outside. The noble gases are noble because they don't react with anything. The reason they don't react with anything is because their outer shell of electrons is full, and they have no need of anyone else because they have everything that an element could ever want. A full outer shell of electrons. Okay? So all of the other elements are trying to get this full outer shell. Well, for sodium, what's easier? Trying to find 7 more electrons to fill that outer shell, or find someone who would like the 1 extra it has? Yeah, give up 1. It's be way easier to do that than to find 7 more. Okay? Luckily, chlorine is in the opposite situation. It's got 7 electrons. It would have to find places to put 7 to have a full outer shell by dropping, or it could pick up 1. Okay? So that's why these two get along so well. Okay? So sodium will donate its electron to chlorine. Now they both have a full outer shell of electrons. Okay? And they're both very, very happy. But they also have what they want. And since they have what they want, they don't have any reason to really stay stuck tightly together. All right? So when you put something like salt, sodium chloride, into water, what does it do? It dissolves highly soluble. Okay? And when ionic compounds dissolve, they actually split into their positively charged and negatively charged ions. Sodium is now positive because it's lost an electron and now has 11 protons and 10 electrons. Everyone follow me there? Okay? Chlorine is the opposite. It now has 18 electrons and only 17 protons, so it's negatively charged. Right? So a solution of salt water will conduct electricity, whereas a container with distilled water in it will not. Okay? Distilled water will not conduct electricity. Tap water will, because there's ions in tap water. Okay? But distilled water will not. Okay? Everyone follow me on that one? All right. So when these two things bond, does that change the physical and chemical properties of the two elements? It does. Okay? In bonding those two things together, we get something completely different than the two things were when they were alone. Sodium is a soft, grayish silver metal that is highly reactive. Okay? I think I told you have to keep it stored in kerosene or it blows up. Right? So it's very, very dangerous. Chlorine is a green gas, okay, that if inhaled will cause the little alveoli, the little air sacs in your lungs, to constrict and you to suffocate. It's the gas they used on the soldiers at Vimy Ridge. Okay? So they're both lethal by themselves. Put them together and we throw it on food. Not that salt's all that good for you, okay, but it's certainly a lot better for you than inhaling chlorine gas or blowing yourself up. Okay, so yeah, it does change. Any chemical bond does change the physical and chemical properties because we have a new substance. We still have the same building blocks, but when they go together, they get new properties. All right, everybody with me on that? Okay. All right. So if we want to name what we call binary ionic compounds, that means they have 2 parts. Okay, we do that by naming the metal first, okay, and then the non-metal. All right, you don't have to worry about cation and anion. That's not that big a deal. Okay, just metal and non-metal for now. Name of the metal is stated in full, unchanged. Name of the non-metal ends in "ide." Okay. So when we had sodium and chlorine together, okay, that stuff is going to be sodium chloride. What's that stuff going to be? Calcium fluoride. How many people wanted desperately to have a prefix on the fluoride? How many people wanted to say calcium difluoride? Okay, there's this natural reaction that we want to do that. Okay, but we don't use prefixes when we're naming ionic compounds. All right, so we might want to write up here, no prefixes. Okay, why don't we need prefixes? Because of the way that nonmetals and metals go together. They have to be trading electrons. All right, which means there's only one way that calcium and fluorine can bond to each other in order for there to be enough electrons to go around. That's the only way. So I don't need to bother telling people that there's 2 fluorines and 1 calcium and calcium fluoride. They know that because it's the only way they can go together. Okay? And it's the same with sodium and chloride. There's only one way those two things can go together and not have any electrons left over, and it's this way. All right? How many people remember the swap and drop or drop and swap in grade 9? Okay? We're going to look at that here in just a minute, but that's the reason why you don't need prefixes. Okay? There's only one way they can go together. All right. All right, let's look at formulas here. Let's say magnesium oxide. All right? I want to write the formula for magnesium oxide. So the symbol for magnesium is Mg, oxide, O. All right. That's my first step. Now I need to look at the charges. Where do I find the charges on my periodic table? Yep, right in the top right-hand corner. The most common ionic charge will be listed there. Okay, you will find that some of the transition metals have more than one possible charge, and we'll talk about that a little bit later on. Okay, but for magnesium, it's a 2+, and for oxygen, a 2-. Okay, do I need to do anything else? No, because +2 and -2 add up to 0. If they already add up to 0, you don't have to do the drop and swap. So doing that one is pretty easy. Okay, but for aluminum sulfide, that one's a little bit tougher. Okay, charge on aluminum is 3+. Charge on sulfur is -2. Now do I need to do the drop and swap? Yeah, because those don't add up to 0. All right, so I take the 3, I move it over and drop it. I take the 2, I move it over and drop it. Obviously, we don't carry the signs down, okay, just the numbers. And now I'm left with Al2S3. I want to double check and make sure that that's right, though. Okay, what does the charge of the whole compound have to equal? 0, right? We said that this one was okay the way it was written because the charges added up to 0. Well, the charges have to add up to 0 no matter what you do. If every aluminum is 3+, and I've got 2 aluminums, how many positives do I have? 6, okay. And same thing here except negative. 2 times negative, or negative 2 times 3 is -6. Still adds up to 0. I'm good. Okay, that's the reason we do the drop and swap. It makes sure that our charges add up to 0 and our compound is neutral. All right. Now, you don't ever have to prove the math to me. The swap and drop works every single time, except once in a while you have to do what with the numbers? Okay, what if I had, I gotta find something that'll work for here. What if I had zirconium oxide? I don't even think that exists, but let's just say, okay? And that shouldn't be capitalized. Okay. Charge on zirconium is +4. Okay. On oxide, it's -2. All right. When I drop and swap, I get a 2 here and a 4 there. What should I do with those two numbers? I should reduce. Okay? Whenever you can, you should reduce. Because, yes, 2 times +4 is +8, and 4 times -2 is +8, or sorry, -8. But if I reduce these down to 1 and 2, it still works. Well, except we don't write 1s. Okay. It still works, right? 2 times -2 is -4, and there's 4+ up there. All right? So always the lowest common terms that will work. That's something that people often forget. Okay? Here's the other thing people often forget. The name of a chemical compound is not a proper name like John Smith or Jane Doe. Okay? It is not a proper name. It is a designation, and thus is not capitalized. Okay? Unless, of course, you're starting a sentence with it. Okay? Then you would have to capitalize it according to grammatical rules, I think. I don't know. Me English, no good. Okay. All right. So when we're using formulas, obviously we balance the charges. That's what we just did. We showed the swap and drop. Okay, that's why we do it, so the charges are balanced. A true compound should have a net charge of 0. Charges are positive on metals, negative on nonmetals, and they're equal to the group number. I mean, we can remember that, except that we made it easy on this, and they actually have their real charges listed in the boxes, okay, which is also nice. Okay, so an example here, we've got aluminum solid reacts with chlorine gas to produce aluminum chloride. Okay, and that would have had to have been dropped and swapped because aluminum is +3, chlorine is -1. Okay, so when we drop and swap, we get AlCl3. Okay, and you notice all the way along here, no capitals. Okay. Question? Why does it matter? Because chemists are funny people and they have to make up rules so that they feel important. I don't know. That's just the rules. Yeah. All right. I want you guys to try 1 through 6. Okay? Writing the names of 1 through 6. Don't go past 6 for now. Okay? We'll check and make sure everyone's doing it right, and then we'll move on to some other ones. Okay, I'll give you a few minutes on that one. All right, so let's have a look at these. Obviously, the first one is pretty straightforward because it's one we did already. Okay, I named the metal first. Sodium, name the metal, non-metal, second, with an "ide" ending. So we're looking at sodium chloride, no capital letters. Okay, for number 2, K stands for potassium. Okay, F stands for fluorine, so we're looking at potassium. That's supposed to be UO. And in the end, you couldn't tell the difference anyway, because my penmanship is so bad. All right, number 3, we've got hydrogen and iodine. Now, sometimes people get a little confused with hydrogen. Hydrogen can behave as a metal and as a non-metal. All right, you see on the periodic table there, it actually has a +1 charge or a -1 charge, because it's equally easy for it to pick up 1 electron and have that shell that can only hold 2 full, or to lose 1 electron and have no outer shell at all. Okay, either way will work for it. So you'll know if hydrogen's behaving as a metal if it's written first. Okay, because the metal is always listed first. If hydrogen is listed second, hydrogen is behaving as a non-metal. Okay, so just in case you're ever confused on that, because it does come up occasionally. Most of the time in an ionic compound, hydrogen is the metal. Okay. All right, for number 4, I've got calcium and bromine. Okay, and again, this number 2 doesn't mean anything in my name because everyone knows that's the only way that those two things can go together. So this is simply calcium bromide. Okay, and then for number 5, I've got aluminum and I've got astatine. So this is going to be aluminum astatide. Okay, and I think actually they've changed it on the periodic table too. Yeah, we say aluminum. That's the right way. But apparently the International Union of Physics and Applied Chemistry says it's aluminium. It's even written that way on your periodic table. But I refuse to drink out of an aluminium can. Okay, yeah, so just so you know. All right, let's have you guys do the rest of them. Okay, finish them up, and then we'll go over them together here in a few minutes. Any questions on those 5? All right, let's look at a few more of these here. Okay, so for number 6, I've got CS, cesium, with sulfur. Okay, so this is going to be cesium sulfide. Okay, for number 7, I've got sodium and oxygen. And again, the 2 doesn't make any difference in the name, so this is sodium oxide. Okay, for number 8, I've got barium and selenium. Now, selenium, you can write the name a couple of different ways. You can say it's selenide or selenamide. It doesn't really matter. Either one would be right. Okay. Okay. For number 9, we've got radium and tellurium, so that'll be radium telluride. Okay, number 10, I've got lithium and fluorine, so it's going to be lithium fluoride. All right, for number 11, we've got rubidium and sulfur, so that's going to be rubidium sulfide. Okay, for number 12, strontium and iodine, so that'll be iodide, yeah, strontium iodide. Okay, for 13, we've got calcium and oxygen together, so that'll be calcium oxide. Okay, and for 14, magnesium and selenium will be magnesium selenide. Okay, questions on any of those? All right. We're going to run into a small problem when naming ionic compounds. The small problem has to do with naming, and that has to do with the transition metals, those ones in the middle. Some of them have more than one possible charge. Okay, and we know that compounds have to come out to a net charge of 0. Okay, so looking at iron here is the prime example. I can have iron with a 2+ charge react with oxygen, which is always -2, and give me FeO, which I would call iron oxide. Here's the problem, though. Iron can also be 3+. And if it reacts with oxygen that's -2, I'm going to get that, which I would call iron oxide. That's a bit of a problem. I mean, it's a bit of a problem if you have two people with the same name in a class. Okay? You have to make sure you go to their last name so that you know who you're talking to. Okay? But in this case, they don't have a last name. So what do? I have to tell people which iron was involved. And if I tell them that, then they'll know what the formula would be. So how do I tell them which iron I used? Right, use a Roman numeral. Okay, so into here, I would put in, for this compound here, this iron oxide, I would put in a Roman numeral 2. Okay, because the iron I used had a 2+ charge. Okay, for this, I would put in a 3. This is going to be iron Roman numeral 3 oxide. Okay, that seems all well and good when it's all set out for you like that. How do I figure out what the charge is, though, if they just give me the formula? Like, let's say I have this. I have lead and I have oxygen. But how do I know which lead I used? Right, choose the one that would make it 0. Here's how you do that. Nonmetals never have more than one possible charge. Okay? Oxygen is always what charge? -2. All right, so if oxygen's a -2 and this compound's set up this way, this has to be a +2. That's all there is to it. Okay, you just got to look at the nonmetal and then figure out what the charge on the other one would have to be. On one like that where they're the same, it's easy, and this is, okay, lead 2 oxide. Right, but you can run into ones that are a little bit trickier, like let's say this one. Okay, Reality is, I do the same thing. Okay. What's the charge on phosphorus? -3. Okay. So every phosphorus is -3. How many negatives are there? 6, because there's 2 phosphorus. All right. So I've got 6 negatives. That means whatever I've got here has got to come out to +6. What charge does every copper have to have in order to make that happen? +2. That's how you figure it out. Okay. Now, a lot of people notice at this point that you could just reverse the swap and drop. And you'd be right about 2/3 to 3/4 of the time. I like to be right all the time. This way works all the time. Okay, if you reverse the swap and drop, that's fine as long as no one reduced the numbers. If they reduce the numbers, you'll get it wrong. Okay, so this way works all the time, right? And this stuff would be copper 2 phosphide. Okay, so the rest of the ionic naming rules still apply. Okay, we still put in the "ide" ending. We don't change the name of the metal. We write it as it is. All we do is add in a Roman numeral. Okay, that is the thing that people will forget on a test. Right? They'll see this and they'll just go, "Oh, copper phosphide," and they'll think they're done. Okay, without looking, because they get confident in their ability to name ionic compounds and they forget to check. Is that a metal that has more than one possible charge? It's something you always want to look for. Kennedy, question? Right. You only use a Roman numeral if the metal has more than one possible charge. Yeah. Okay. Everybody's clear on that one? So you don't have to use it all the time. Okay. If you got sodium and chlorine going together, you're not going to write sodium 1 chloride. You don't have to. Okay. Sodium's only got one possible charge. It's redundant then. Okay. All right. These ones all involve the use of Roman numerals. Okay, I want you to do the first 5. All right, then we'll go over them together and check and see if we're doing them right. Okay, let's look at the first couple here. So we've done this one already, okay, but we'll do it again just for the sake of doing it. Okay, we always look at the non-metal. Okay, oxygen's a -2. Okay, so that's +6, or sorry, -6 here. I need to make +6. That means iron has to be +3. So this is iron 3 oxide. Okay, for number 2, I've got cobalt and sulfide. Okay, sulfide's a -2. Cobalt must also be a -2 because they're 1 to 1 here. Okay, so I'm going to go with cobalt 2 sulfide. Okay, for number 3, I've got manganese chloride. Okay, but the chlorine has a -1 charge. Since there's 4 of them, that must mean that manganese is +4. So we'll have manganese IV chloride. Okay, for number 4, we've got copper and sulfur. Sulfur's -2. Copper can be +1 or +2. In this case, it must be +2 because they're 1 to 1. Okay, and for number 5, we've got tin and tellurium, and this is one of those ones that can trick you because this one may have been reduced. Okay, tellurium is -2, right? Okay, so if tellurium is -2, I've got 4 negatives here. That means that tin must be +4. Okay, so that's one of those places where reversing the swap and drop would result in the wrong answer. All right, so it would have worked 4 out of 5 times. Okay, on that set of 5. All right. Actually, sorry, it would not have, because it would have got you the wrong answer. 1. It would have got you 1 here and 1 there too, if you'd have reversed the swap and drop. So yeah, don't reverse the swap and drop. It just doesn't work 2 out of 5 times. Okay, so yeah, do it this way. How are we doing on that? Is that making sense? Okay, let's finish those ones up. We'll go through the next 5 here in a couple minutes. All right, so for number 6, we've got mercury and astatine together. Okay, astatine is -1. Okay, so that makes mercury a 2. Okay, so we've got mercury 2 astatide. Okay, for number 7, we've got polonium with iodine. Iodine's a -1, so polonium must be a 4. Okay, we've got antimony with sulfur. Sulfur's a -2. Okay, so that makes 6 negatives, so antimony must be a +3. All right, so we got antimony 3 sulfide. Okay, and again, remembering there are no capital letters on any of these. Okay, and number 9, I've got nickel and nitrogen. Nitrogen's always a -3, so I've got 6 negatives. I need to have 6 positives, which means nickel is 2. And that's nitride. Okay, and then I've got ruthenium with oxygen. Oxygen's a -2, so ruthenium must be 4. Okay, making sense? All right, one last little new trick for you and these has to do, with the use of polyatomic ions. All right, so if you look up here on the top of your periodic table, okay, you've got this table of common polyatomic ions, and we are not going to get to that today. Okay, I'll talk about it, but we won't get to practicing it. Okay, these ions behave as though they're elements. They don't break up, they stay together. Okay, so if I have something like this, let's say that particular compound, I have sodium, and it's with NO3. What's the name of NO3 according to your table of common polyatomic ions? Nitrate. So this stuff is sodium nitrate. They're actually easier to name because you don't have to think. You just have to read the name right off there. You don't have to change it to "ide," nothing. Write it exactly like it is on there, and you've got it down. Okay? So writing the names is pretty easy. Sodium nitrate. Okay? But if I gave you something like this, tomorrow, we'll figure that one out. Okay? All right. Have a good day, guys.